All right, guys. Today, limits analytically. Finally. So you understand by this point how to find a limit through a graph, through a table, right? So the most efficient way to do a limit should be algebraically speaking. Fair enough? So that's where we're at on the course. Okay? Now, in order for you to fully understand why the things that we're gonna do work, I'm gonna refer you back to something we talked about last class, which was this following limit. That. It was like property number 1 or 2, I don't remember what it was. Cool. Do you remember what the answer was?
C.
Okay, but tell me why. Why is the answer C?
Because in a y and an x, the y is equal to the x. So
Okay, so first thing, on y equals 2x, literally, I am saying y is equal to x. If x is 5, y is 5, and so on, right? Okay, that's one of the reasons. What else though, as far as the limit goes?
that's
Yes.
Is it because it's like a linear equation that passes through the origin? Holding like,
It's a linear equation that passes through the origin. Is like you're saying that's the reason why it's C?
well,
So not necessarily because it passes
Yeah.
through the origin, but what do we know about the function itself? Say it louder. It's continuous. So let's discuss this real quick before we even go any further with anything today. If you have a continuous function, does that mean that every single point on that function exists? Yes. That's what it means, right? And if every single point of that function exists, then will the limit also exist? Yes. And will the limits and the points be exactly the same? Yeah. So, would you be okay saying that you're 100% positive that if a function is continuous, the limit will be exactly the same as the point? You guys with me? So that's why it's very easy for me to say, since this is a continuous function, even though I'm talking about the limit, I can just literally just plug in C into here, which produces a C value, which is the output. Does that make sense? Cool. So what I'm trying to tell you is, today, we're gonna be utilizing, like, if I give you this function, we're gonna be utilizing this a lot. Which is not really the limit. You're looking for the points, the value. However, again, let me rephrase this one more time. If a function is continuous, the value should be the same thing as the limit. Make sense? Now, what if this doesn't exist? Could the limit still exist?
yes.
And that's what we'll explore today. Like, what happens when, like, if we algebraically try to figure this out, but it's just not happening? Then there is a limit, but how do I figure it? Fair enough? So in other words, in order for us to find this, we use something called substitution, right? Like, if I give you a function and I give you an x value, you substitute the x value, that's how you find the point. If you use substitution and you get a value out of it, that means that the function is going to be continuous, and if the function is continuous, then the limit has to be the exact same thing. Easy enough? Alright, example 1. What is the limit as x approaches 1 of x squared plus 2x plus 1? Okay, based on what we did last class, I could split this up into a bunch of limits. Remember that part? Using the properties? Let's not. Go, that's what last time, so that you can practice for this. Essentially what he told you is that I could just take the limit of this first, and then add this, and then add this. But let's ignore the limits. Let's talk about, could I just figure this out? Which in this case would be, what is f of 1? Which in this case happens to be 4. What does that tell you about the function at 4? It's continuous, and if it's continuous, the limit would also be the same. So therefore, this would have to be 4. Done. Easy. Right? So let's discuss this. Your first strategy for limits analytically, even though technically what I'm doing is this, if you really think about it, is to use substitution. You're literally going to take the value, you're going to plug it in. If it results on an actual number, you're done. Congratulations, that's the limit. Move on with your life. Fair enough? So, I don't have a bunch of examples of this. I don't think we need a bunch of examples of that. You know how to plug in a number. Cool? Alright, example 2. Let's take the limit. As x approaches 2, of x squared plus 4x minus 12 over x squared minus 2x. Okay. Right. Substitution. You don't even have to ask yourself. You can if you want, by the way. Like, is this continuous before you even start? But don't worry about it. If it's not continuous, something's gonna tell you that it's not. Ready? Top. 2 square is 4. 4 times 2 is
8.
so that so far I have
0.
minus
0.
12 is 0. Can I have a 0 in the numerator of a fraction?
Yes.
We're good so far. Alright, denominator, 2 squares 4 minus 4. So this is what I meant. If this was a continuous function, you would have gotten a number. We're good to go. We didn't. Now, luckily for you, we've already encountered this type of situation in this class. We've already kind of discussed what it meant. Right? What does this mean? What is it? There's a hole in the graph. Even though I don't have the graph to look at it, if you get a 0 over 0, you have learned in algebra that that means that there's a hole in the graph. So I'm like, okay, there's a hole in the graph. Okay. Now, it does have a name, so I need to share that with you. If you get a 0 over 0, it's called an indeterminate. Form. Cool. It's not the only type of indeterminate form. At least for today, that's the only one we're discussing, but there are more. Cool. But more important, what I need you to know is I don't really care too much that you know that it's called indeterminate. I need you to know that that's a hole. Because then the question is, even though I have a hole, does the limit exist? Yes. So there is an answer to this, 100%. The question is, how do I find it? Okay? And the answer to that has nothing to do with calculus. It has to do with algebra, which is how do you find holes? Go back to your knowledge of algebra. And you gentlemen said that I would have to use factor to see where the hole is located. So look, I'm not teaching you any calculus really today, but I'm being completely honest with you. You already know what a limit is. That's the calculus component of this. It's just algebra today. All right, so what does the denominator factor into?
X and x minus 2.
Okay. Before I go any further, if I look at those factors, why does it make total sense that I'm getting a 0 on the denominator now that I look at it this way? Because one of the factors is x minus 2, which means logically speaking, let's say, I'm not saying that you don't, but logically, if you don't know how to factor the top, you at least gotta know that x minus 2 is on the top. Right? But that's a whole different conversation. I'm assuming we know how to factor. So what are the factors on the numerator?
Plus 6 minus 2.
X plus 6 times x minus 2 divided by that. Are we good? What's up? Is it recording? I hope it's recording. Yes? Okay, cool. Alright, we're good? This cancels out. I'm gonna get lazy, but you can rewrite this statement if you want. Cool. So then what do you think? How do you proceed from here?
Substituting.
Do you now just try again and you just do substitution? Cool. So the top will give me 8 over 2, which means my limit is 4. Now, I know that this is not what we're talking about, but if I were to ask you, what does the graph of this look like? What does this information tell you about the graph?
Asymptote of 0.
Well, think about why you had to cancel. You told me there's a hole. Specifically where? At 2, 4. So if we're talking about graphs, which is not what we're doing, but if we were, what you figured out is that there is a hole specifically at 2, 4, but the limit exists there, right? Even though the value is not defined. Make sense? Alright, how we doing? Alright, let's try another one. what is the limit as x approaches 4 for x minus the square root of 3x plus 4 over 4 minus x. Cool. So example 3. All right. What do you guys think? It's also undefined, but is it 0 over 0 or is it something over something else?
The number over 0.
It's still 0. Is it 0?
Zero.
It's still 0, 0?
Yeah.
Okay, beautiful. If we're kind of lost, 12 plus 4 is 16, square root of 16 is 4, 4 minus 4 is 0, 4 minus 4 is 0. Fair enough? Okay, there's a hope, 100%. So there's gotta be a solution. How is this problem different than problem 2?
That was
Yeah.
a factor.
Okay, so this one is something that you can factor because it's a polynomial, and it was easy to, in my opinion, factor. We're technically gonna have to factor here. It just doesn't seem like it's gonna be easy because it's not a polynomial. Are you guys with me? But I technically need to find a factor. Specifically, like a 4 minus x on the top somehow. Get a little complicated to think about it that way. So now, what bothers me a little about here is that if I'm gonna factor, it's the square root. So I'm not gonna be able to factor something like if a square root is present. So I guess I gotta figure out a way of algebraically somehow maybe try to get rid of that root somehow. Cool? You got something? Conjugate. Okay. So in algebra 2 you learn something called a conjugate. Now specifically we're gonna focus on the conjugate here because we have something known as a binomial, which means I have some term, either plus or minus a root. Cool? We're gonna put the conjugate in action so you can understand why we're using the conjugate. Okay? Alright, so this is the limit as x approaches 4 of x minus square root of 3x plus 4 over 4 minus x. But when you say conjugate, what conjugate am I using?
That's power
The top, so what would it be?
x.
X plus 3x.
Okay? And then x plus as such, right? Why do I, just making sure, because I've seen this mistake happen. Some people say the conjugate, you just gotta switch the signs. Be careful. I don't need to switch this sign. I need to switch the sign that is in between the two terms. Cool? Alright, so by multiplication, numerator wise, what happens?
X squared.
So x times x is x squared. Beautiful.
You cancel out the other 2 and 2.
Okay, cool. So I'm gonna explain it in the video, but technically I never do this with conjugate. When you multiply the inner with the outer for both of them, they're gonna produce the same thing with opposite signs. So that's the idea of a conjugate. It will always cancel the middle term, so you can kind of skip that step. Cool? So then the only thing that's left would be for sure minus, and then I'm gonna put parentheses so that we don't make a mistake. Right? Make sense? Alright, so that's the top. I'll clean up in a second if I need to. And then the bottom, I have this idea of 4 minus x. Gotta put that in parentheses. And then x plus the square root of 3x plus 4. Why do you think that I personally decided not to actually distribute this out? Not only can I cancel it, I want to cancel that, right? Remember, this is what got me a 0 at the bottom, right? So if I want to cancel it, then why would I distribute? Make sense? All right. The top, the parentheses, necessary?
No.
Yes.
Negative.
Because that's going to have to distribute out. Oh, so I'm going to get a little lazy here, so I'm going to distribute, get rid of that, and this becomes a minus. Agree? All right. Does that factor? Yes? Okay, so limit x approaches to 4. Denominator is 4 minus x. X plus square root of 3x plus 4. What's the numerator factor into?
X plus 1, x minus 4.
X plus 1, x minus 4. Agreed? Okay. This is one of those things that I see it, but some students sometimes make a tiny mistake. Oh, what's up?
Oh,
What do you think?
you just have to just take out the negative.
So I know these are almost the same. You can learn out the same. So if I need to match this, then I actually need to either do one of those two things. Factor out a negative from here, or factor out a negative from here. Cool? Alright, so what would you rather do? The negative in the bottom or the negative in the top? Bottom. So if I factor out a negative here, this becomes negative, this becomes negative, this becomes positive. So then x minus 4 and x minus 4 would cancel out, but now I still have this negative down here, right? And that cancels. Okay. So what do you think? I don't have a lot of room, but can I use substitution now? So as x approaches 4 for x plus 1, that gives me 5. I'm going to throw the negative here, even though it's at the bottom. Cool. And then the bottom, I got
Negative 8.
positive 8, since I put the negative on the top, right?
Oh.
Yes? No? Cool. If anyone's lost, this would give me a 16. Square root of 16 is 4. 4 plus 4 is 8. So then my final answer to the initial problem is that the limit as x approaches 4 is negative 5/8, which once again, the fact that I got a 0 over 0 means that there was a hole. So graphically speaking, I have a hole at 4 comma negative 5/8. Cool? Alright, how are we feeling about this? Are we okay? So far, if you really think about it, I mean, the 3 examples we gave you is like, okay, best case scenario, you substitute, you get a number, we're done. Fortunately, based on the last 2 examples, is like we get a 0 over 0, that means it's a hole. But I want you to think, I haven't taught you any calculus, all we've done is algebra. Things to consider is maybe factors. If factoring is not an option, maybe I can use this idea of conjugate. Cool? I'm going to show you a 3rd example of something else you could do, and then we'll move on from this idea of 0 over 0. Cool? Alright, so the next thing, or the next problem I want to try would be what's limit x approaches to 0 all over x. Okay. Still 0 over 0, right? Okay. Factoring an option? No. Conjugate an option? I mean, technically, I guess yes, because like I have a binomial, so I can multiply by the conjugate, but all that's gonna do is still gonna have a 2 plus x at the bottom, but now it's square somehow. That's still probably gonna give me a problem if I plug in, because I want to have a 0 on the bottom still. Fair enough? So I don't really see how the conjugate is gonna help me. And if I'm being honest with you, my feedback is I only really think of conjugate if there's a root involved with the binomial. Cool? So now, again, no calculus, just algebra. What could I do algebraically?
Partial fraction.
Partial fraction? Oof. I could try, but before I even try that, honestly, partial fraction means that you want to take one fraction into multiple. There's already multiple fractions there, in a way. It just happens to be that there's multiple inside of one big fraction. Yes?
Can you multiply the numerator by 1 over x and then make it a common denominator?
Okay, cool. I'm gonna be honest with you. I'm just looking at this, and here's what I see. I see a subtraction of fractions. I see a division of fractions. So how about I actually just subtract the fractions, divide the fractions, so I can actually just get one fraction instead of all this mess. So in other words, what am I trying to tell you is like, do operations. Do the operations that are present if you can, which in this case, can you do it? Yes, if and only if I get, in your case, you said, I need a common denominator before I can proceed. Cool. What's the common denominator?
2, 4.
So for this, I'm gonna leave that x alone. It would be 2 times 2 plus x, right? Like that. If I do that to the first, this 1 becomes a 2. And this 1 becomes a 2 plus x. So I'm gonna leave it like that for the moment. Cool, parenthesis is totally necessary, right? Bless you. If I clean up that top fraction, what do I get on the top fraction? So this 2 minus 2 is gone, but I have a negative x. So I have a negative x divided by 2 times 2 plus x divided by x. How do I divide fractions? Keep change flip. So I'm gonna get lazy, I'm gonna rewrite this. Instead of dividing by x, I can multiply by what? 1 over x. What does that help you do?
Cancel that.
Yeah, the x can cancel this x because these two things are being multiplied and this is divided, so they undo each other, leaving me with negative 1 over 2 times 2 plus x. Right? Substitution. That's just a negative 1, right? There's nothing to substitute in there. 2 plus 0, 2. Agreed? Final answer is that the limit as x approaches 0 for the initial function is negative 1, 4. Which, once again, I sound like a broken record, but I have a hole at 0 comma negative 1. And once again, I know I have a hole because it's 0 over 0. Okay? How we doing? We're good? Alright. I think we've done enough practice with the idea of the hole. Let's discuss it. What other discontinuity could occur that is not a hole? An asymptote. Specifically, vertical asymptote, because we're talking about x approaching, right? How are you going to know that you're dealing with a vertical asymptote instead of a hole?
Something over 0.
It's a number over 0 as long as the top is not 0. So if you're still getting a 0 in the bottom, but the number on top is no longer a 0, then it's 100 an asymptote. Now, before I even do an example, vertical asymptotes, think about the graphs that you studied in Algebra 2. Most of those graphs, as they were approaching a vertical asymptote, what do?
Go to.
They either go up and one goes down, or they both go up, or they both go down. So then you should be expecting your answers to be, let's first, before I even try an example, if you have a graph that's doing this, then your limit is undefined, non-existent. Infinity? But I got a question. The definition of a limit is that you have to get to a unique value. Am I going to a unique value? Infinity is not a value. So technically speaking, I'm just being completely honest with you. Technically, you're supposed to say it doesn't exist. Technically. But for this class and for the AP curriculum, I need you to know that if they are both going to infinity, you're gonna call it infinity. Yes?
So, like, let's say if they ask you that on the AP exam, like, what would I say? Would I just say it's
If they're both going to infinity. Cool? They're both going down. The only time you'll say it does not exist is they are actually going in opposite direction. But if I'm being completely honest, out of all the textbooks I've read for calculus, all of them say that you're supposed to say it does not exist.
I think on the website it asks you to say it.
I know. Cool. And that's why I think that's why we use the Larson textbook. I'm gonna be honest, because it kind of matches what we need you guys to do. Cool? Alright, we're good? So now we're ready to try a problem. Here we go.
I like your shirt.
What's that?
I like your shirt.
Yeah. Go Chelsea. I know everybody thinks it's Target, right?
I thought it was Target. I need to
Alright, let's see if I can come up with one. So x cubed plus 1.
I don't like this shirt.
X minus 1. You don't like my shirt? Too bad. Alright, ready? Okay, so now this problem. Plugging in. Substitution gets what?
2 over 0.
2 over 0. What we just had a discussion about is this is not an indeterminate form, okay? Now it's a vertical asymptote. Cool? Alright. Now, again, based on our discussion, I could graph this and I could try to figure out what's going on, but today's lesson is about teaching you how to try to do this with algebra. Okay? So here's the problem. Based on our conversation, because infinity is not a value, it's not like substitution is really going to be something that I can use. And also, it's not like anything's going to cancel out. Are you guys with me? So I'm going to have to get creative about how I attack this. And what I'm going to have to do is that the definition of a limit says that in order for it to exist, there has to be a left and a right side approaching the same value. Well, because I'm not going to actually be able to do anything with numbers, I'm going to actually have to split it up. into a left and a right side. So here. But I don't want to make a graph or I don't want to make a table, so I want to still use numbers. Pick a number that is arbitrarily close to 1, but from the left side. 0.99 with a whole bunch of numbers. Yes? And use that as a substitution. Now, what is 0.999 like to the third power? So some people in other classes were like, oh, I don't know, how do I do that? Okay, let's be honest. Was the numerator really a problem for us here? Not really. I don't need you to know exactly what 0.99 whatever is to the third power. Do you agree that 0.99 is so close to 1 that I can almost say like I'm using 1? So 1 to the third power we knew was 1, and adding 1 was 2. So even though I'm using 0.999 cubed plus 1, I should be very close to 2. You guys with me? So I'm going to use this, I'm going to switch this and say like an approximation because I'm using numbers. But I want to say it's fair to say that it's 2. Oh, and I'm being honest here, I didn't really care too much about the numerator. That's not my problem. The problem was the bottom. Oh. 0.9999 minus 1. What's going to happen? It's going to be negative, and then depending on how many 9s you use, eventually a 1. Alright, so I'm just going to put dot, 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 1. Cool? So first thing I'm going to analyze is the fact that I have a positive divided by a negative, which will allow me to know that this is negative something. Cool? Now, even without me doing the operation, I already know because I've graphed enough, and hopefully so have you, that I knew I was looking for an infinity or a negative infinity. So even if I didn't really know how to do this, I'll be like, okay, I'm going to guess that this is negative infinity. But let's discuss why. The negative part you get. Do you guys agree that if I had 0.1 as a fraction, that would be 1/10? So then it would be 2 divided by 1/10, which is 2 times 10. If I had 0.01, it would be 1 over 100. So then it becomes multiplying by 100. So the more zeros I get, then the bigger that becomes. So it's now like 1,000,000, right? So now I'm doing like 1,000,000 times 2. And then like 1,000,000,000. So it's all it's doing is getting bigger and bigger. Make sense? All right. With the same logic, would you agree then that this would be still approximately 2, even though it's a little bit more than 1. But what's going to happen when I do a little bit more than 1 and take away 1? Positive. And with the same logic that we just discussed, this time is going to be positive. So now the fact that the left and the right are approaching different infinities in this case, and I can go back to the original and say, does not exist. Cool? Questions, guys? Are you sure? Okay, so I mean, I have more examples of this, but would you like me to do more? Do you feel like you understand what's going on?
Is this all? Like there's no more content?
No, there's more content. But at least as far as like where we're at, right? So we said 0 over 0 is whole. Number over 0 is vertical asymptote. So would you like me to show you another example where there's a vertical asymptote, or do you feel like you understand the idea here? One more? Cool. Let's see what I got here. Can I erase? We good? Actually, let me do that. Okay. One more here. Little change, something new I haven't asked in the past 5 examples. This time, from the beginning, it's a one-sided limit. That's it, that's the only difference, right? So this will allow me to tackle 2 things. Something new, as well as giving you another example with asymptotes. Cool. Even if it's a one-sided limit, guys, you can still just use substitution. Tell me why.
Because it's approaching from both sides, and it's definitely approaching from one side.
Okay, exactly. So listen, if it was continuous, if a function is continuous, would the left side and the right side be approaching the value that the actual points? So how do you find the point? You plug in, right? So it doesn't matter that it's one side or the other? No. If I had a hole, same thing, the limit would exist, right? But I can still figure out whether it's one side or the other. So in other words, I can still use substitution, no big deal. Oh, all right, by substitution, what happens here?
You get 5 over 0.
So I get pi over 0. The sign of pi is 0. Therefore, it's going to be a vertical asymptote. Cool? All right. Now, the fact that from the beginning this is a one-sided limit, there is an answer. It's either infinity or it's negative infinity. Cool? You could guess. It's a 50-50 shot. I won't give you credit though. You just guess. So what would you do to try to figure this out?
I just do pi plus 180.
Do pi plus what? I'm sorry?
Pi plus 180.
So like a little bit more than pi. Okay, so this is where, I mean, an approximation of pi is typically, most people say is 3.14, right? So as long as it's a little bit more than that because it's from the right side, right? So I don't know, 3.15 or something-ish, right? The top is not the problem, remember? Right? Like that's not really the problem. So I can say it's approximately pi on the top. Yes? The question is, how do I take the sign of a number that's a little bit more than pi?
It'll just be below where pi is in the circle, so
Okay, let's give a visual. So unit circle wise, here's pi. And the location of pi on the unit circle is -1, 0. And we know that the x-coordinate represents the cosine and the y-coordinate represents the sine. That's a whole nother discussion, right? You are telling me to pick a number that's a little bit more than pi. I'm gonna exaggerate it so you can actually see it. So I'm gonna say, like, let's say I pick this angle right here. It's a little bit more than pi. Do you guys agree that that's gonna give me, I don't know, some x-coordinate, which I have no idea, but it's also gonna give me some negative y-coordinate. But it's gonna be so tiny that I'm gonna approximate it that it's -0.000000 with a 1 on it. And based on what we did earlier, when I take pi and divide it by a negative, and it's such a small number, then what's gonna happen?
negative infinity.
Cool? Questions? Are you sure? Okay, for video purposes, I'm gonna end this video here. I think this would be like based on how you learn in other classes. This is typically what the lesson would be here. So I'm gonna go ahead and end this video. You can stop for me. And then we're gonna take a break and then continue. Cool?